Hello everybody, so we're going to look at solving some quadratic equations. And this is a real world example. This is something that I actually did as an engineer. Uh, when I would look at a concrete beam, so I designed bridges and buildings and things, and sometimes we have concrete beams in buildings and bridges that support the load from above, so the roof load or the bridge load. So there could be a uniform load on it, and I'm just going to make up a number here, but let's say the bending demand on this. So the bending is like where it wants to bend, right? So at the bottom edge of the concrete, it wants to tear apart, and at the top edge, it's pushing together. So the way that concrete beams are made is we have reinforcing steel put in them. So maybe you've seen rebar on the side of the road or something like that. So the rebar gets put in there to help that tension because concrete isn't very good in pulling apart, right? But steel is very strong and helps the concrete stay together. And concrete is very good in compression, so it kind of supports the top compressive part while the steel works together to keep the tension part together. So this is kind of how it would look if you cut a beam in half. You'd see the steel as circles on the end, and what they do is they're providing the tension just coming out of the page like this. So there's tension like pulling on that rebar. So what we do when we design these beams is we figure out what is the demand, how much bending moment is being put into that. That's kind of a function of the force and how much span there is. So I don't know if this was like 40 feet or something like that. And say I figured out that the moment demand, so mu is, we'll just say 200 kips. Kips is 1,000 pounds, so 200,000 pounds per foot or times foot. So this is a unit of moment, kip feet. Okay, so now say I wanted to figure out what the area of steel I needed for this beam, and let's say I wanted the dimensions of the beam to be 2 feet tall, so we'll say 24 inches, and foot wide, so we'll say 12 inches. Okay, so this is kind of something that engineers guess and get kind of an intuition about when they've done a lot of beams in the past. So we usually make a guess on what dimensions we want to use, and then we figure out how much steel needs to go in there. And then if the steel is just way too much, then we might make the beam deeper or wider or something like that. Okay, so this is called, we'll just call this the depth of the beam, D. And it is technically to the depth of the steel. So let me say that's 24 inches. So this is my value D. And then the width of the beam we'll say is B equals 12. So that's where these variables come in. So this is going to tell me the capacity of the beam, and then I need to make sure that it's going to be able to support that weight. This phi number is just a safety factor, and we just say 0.6. And so the area of steel is going to be unknown. Fy is just the yield strength of the steel, so it's typically 60,000 kips per square inch. Okay, and then I multiply D, which I guess is going to be 24 inches. So right now I'm going to try to put everything in kips and inches, just so it works out. So this is in inches, and then this area of steel is unknown, and then this Fy is 60,000 pounds per square inch, but 60,000. So instead of 1,000, I'll say kips per square inch. And this is going to be divided by 1.7, and then F prime C is the compressive strength of the concrete. We'll say is 5,000 ksi or 5,000 psi, so that'd be 5 ksi. And the width of the beam we said is 12 inches. So this will give me the capacity of the beam. Now I want it to be approximately equal to 200 because I have the safety factor built in. So this actually turns out to be a quadratic equation because let's just pretend for a moment that this is just x times some number times some number. We'll just say, I don't know, h minus some other number, k, x, right? Because all of this is just going to be some number. And so when I multiply it out, I get hax minus a k x squared, right? And then I just have another constant on the other side. So let's just group all these numbers together. And I'm just going to speed up the video and do it real quickly. Okay, now I want to group these a sub s's, and I want it to be in this form. I want to get to ax squared plus bx plus c equals 0. So I want to put the x squared term over here. So my x is really a sub s. So I'll go ahead and do that now. Okay, so I multiplied. Now I have my a sub s's. Now I'm going to group them on the other side. So I'm just going to add 21.168 to both sides, as squared, and subtract from both sides 864 a sub s from both sides. So it brings it over to the other side as negative 864 a sub s plus 200 equals 0, right? Because I added 21.168 a sub s squared to both sides. So now I have this in my form. And here's my a value, my b value, and my c value. So a is 21.168, b is negative 864, and c is 200. So what I'm going to do is plug these values into the quadratic formula. And like if I wanted to solve this using one of my other methods, like trying to complete the square or trying to factor this, I mean, can you imagine trying to factor that? It'd be extremely difficult. So instead, we're going to use the quadratic formula. We just plug these values into this quadratic formula that says x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So it's going to make it a lot easier to solve, and actually instead of x here, I'm going to use a sub s. So I could get two values of a sub s. Probably one of them won't work just because of the physical nature of the world. You can't have like negative area or something like that. So we'll see what happens when I plug in those values, and I'll just go ahead and do that on the calculator. So here I'm just going to set a equal to 21.168, and I'm going to set b equal to negative 864, and I'm going to set c equal to 200, and that's that. So now I'm just going to find out what is the value of negative b plus square root b squared minus 4 times a times c, oops, and then I want to divide all that, so I need to put parentheses around everything. So parenthesis there and parenthesis there, divided by 2. Oh, I want to make sure I divide the whole thing by 2 times a, so put parentheses around 2 times a, and it gives me 40.5. That sounds really big. Oh, the reason for that is probably because this was in kip feet, and I want it to be all in inches. So I actually need to multiply this by 12. So this 200 should be 2400. Let me see if that changes anything. So C equals 2400. And then let me repeat that. Yeah, so well, 37 is still a big number. 37.8 inches squared. So this is maybe a bogus number. And let me look at the when I subtract. So instead I'm going to subtract the square root. And that looks a lot better. So this is 2.99, call it 3, right? Call it 3 inches squared. So Yeah, and that would just be a little bit conservative if I added a little bit more. So 3 inches squared of steel is what I'm going to use. So this is probably way too much steel, right? It's probably even bigger than this section. What is? Well, it's not that, but it's about 1/4 of the whole section. So really, that's a lot of steel. So this is kind of my bogus answer. It would probably, give me a solution to this quadratic equation, but it's not really useful in this situation. I would much rather use 3 inches of steel than I would 40 square inches of steel. Okay, so that's just an example of a real-world problem where you really do need to use the quadratic formula to solve this sort of thing. And it is useful in the real world, so surprise, surprise.